everyone, welcome to the course on medical biomaterials. Now we will start a new topic that is called ceramics. Ceramics is also a medical biomaterial, just like metals, polymers, both synthetic and natural. Ceramics are finding a lot of applications because they have a very useful property like osseointegration, biorecognition and so on actually. As you know, bone contains lot of ceramics. In fact, the material, the bone is made up of hydroxyapatite. Hence, ceramics oxides, different types of oxides like alumina, zirconia, they are all finding applications in the area of medical biomaterials as a spacer, as a filler, as a coating material and so on actually. Okay, if you look at bioceramics, alumina, that is aluminum oxide, is a ceramic material which finds a lot of application. Zirconia, for example, okay, zirconium oxide, silicate glass, that means SiO2. So, there are different types. Then calcium phosphate, that is the apatite. Okay. In fact, our bone contains a lot of this. Calcium carbonate, hydroxyapatite. Okay. So, all these are ceramics which are finding a lot of application. In fact, this picture is of hydroxyapatite. Calcium sulphate, it is used quite a lot in orthopedic for filling. For example, this picture if you can see, there is filling which needs to be done. So, they use calcium sulphate and some of the bone ground bone material and they fill it up here. So, not only it gets integrated, it is highly biocompatible, it prevents bacterial infection and so on actually. So, these biomaterials, these bioceramics are extremely biocompatible and they can be nicely integrated, especially in dental applications, in orthopedic applications. Of course, they have certain shortcomings, especially they cannot take tensile force and they do not have a crack propagation resistance. So, these are some problems of these type of material, but then they have quite a lot of advantages which are now being exploited in the area of biomaterial. So, we will look at some of these in this particular class. So, lot of advantages, they have a high compression strength, they have good wear and corrosion resistance. So, for example, if you take metals, chances are either there could be oxide corrosion or bimetallic corrosion or wear corrosion, whereas these material do not wear so easily. They can be highly polished, they are bioactive, bio-inert and osteointegration properties, all these are advantages of bioceramics. Now, of course, it has some disadvantages. High modulus, so mismatched with the bone, okay, the modulus has to match with the bone, otherwise you end up having stress shielding. That is why nowadays titanium based material alloys are coming where the modulus is coming closer and closer to the bone. Low strength in tension, it just cannot take tension, it will just snap. Low fracture toughness, that means if there is a crack, it propagates very fast and the material will break, whereas if there is a crack in a metal, it has got very high fracture toughness, the metal will still survive for a very long time. Difficult to fabricate, okay. So, metals, polymers can be fabricated to any shape, size, dimension, but these are a little bit more difficult to fabricate. So, these are some disadvantages of that. Okay. They are bioactive, they integrate very well, as the name implies, osteo, so that means with the bone they integrate very well. So, they form a good bonding between bone and material will be formed, a chemical bonding, whereas if you put in an inert material then it will be separate, the material and the bone will be separate, so they do not integrate, whereas a ceramic material integrates very well. They are bioactive like hydroxyapatite. Okay. There is a good contact between bone and the implant, so osteointegrate, especially like titanium. Okay. So, ceramics have all these good properties. If you take alumina, that is Al2O3, zirconia, that is a zirconium oxide, and carbon are bio-inert. Okay. So, they do not cause any adverse reaction to the host system. If you take bioglass or glass ceramics, bioglass, that means SiO2, silicon type of material. They are bioactive, okay, that means they take part in the integration process. If you take calcium phosphate ceramic, they are bioresorbable, that means they will completely disappear over a period of time. So, if I am going to use it for filling, bone filling, when the bone starts growing, this will completely get resorbed, or if I am using it for scaffolds, it will get completely resorbed. Okay. So, that is beauty of calcium phosphate. Bioglass and glass ceramics, they are non-toxic, they chemically bond to the bone. So, they do have good advantages. Okay. If you take glass ceramics, they could have osteoinductive property. Okay. So, that means they will allow cells to proliferate. Calcium phosphate ceramics, like I mentioned, exhibit non-toxicity tissues, they get bioresorbed, and they also have osteoinductive property. Zirconia ceramics, okay, they are bio-inert and they are non-cytotoxic. Carbon is also used nowadays. They have good mechanical properties of the bone, they elicit blood compatibility, no tissue reaction, and non-toxic to cells. Okay. So, carbon is also very good, which can be used in some biomedical applications. So, you see a lot of these properties come into picture. Bio-inert if you are interested, or if you want to have a osteoinductive property, or if you want osteointegrative property, okay, we can, if you want bioresorbable property, then we can have different types of ceramics. This particular table I showed long time back, comparing ceramics, metals and polymers. As you can see, hardness, ceramics have very high, metal have low, polymers are very low. Elastic modulus very high, polymers are low. High temperature strength, high, low, very low. Thermal expansion, it does not expand at all, whereas metals will have very high thermal expansion, polymers also can have. Ductility, it is very low, because we can't make shapes out of it, ductile. Corrosion resistance, ceramics have very high corrosion resistance when compared to metal or polymer. Resistance to wear, again it is very high. Electrical conductivity, it may, because you can have ceramics with conductive and or non-conductive properties. Metals high and of course polymers low. Density, it is very low, metals will be high, polymers will be very low. Thermal conductivity, it can have thermal conductivity just like electrical up or down, metals will be high, polymers will be low. So, this table gives a very nice comparison between all these three major classes of biomaterials. So, this picture if you see stress strain diagram, metal you will have the elastic region, then the plastic region. Polymer, as you can see, it can go like this. Ceramics, whereas it will have high modulus, it will have very poor crack propagation, I mean it will have very high crack propagation. So, it does not, it is not tough, so it does not take a tension. Okay. So, it cannot be used in such applications, it will just snap here, you do not see a plastic region at all, unlike metals. Okay, that is the stress strain diagram. This is also a very interesting picture taken from this reference. If you compare the Young's modulus versus fracture toughness, as I mentioned, what is fracture toughness? If there is a crack that is developed, how long can the material last, or if the crack starts propagating very fast and the material fails, that is called fracture toughness. Okay. It has got this particular units, megapascal meter per half, as you know Young's modulus as gigapascal. So, if you look at materials, okay, like eggshell, hydroxyapatite, silica, ceramic, they do have good Young's modulus, compressive Young's modulus, but their fracture toughness will be very low. That means, if there is a defect or a crack that is formed, the material will fail immediately, I mean comparable to your bone or dental material. Whereas, if you take metals like nickel, chromium, stainless steel, they have very high Young's modulus, very high fracture toughness. Zirconia, of course, not bad, it is coming up in fracture toughness. Okay, but these are the metal area, you have amalgams, then we have titaniums. So, if you look at zirconia or bio silica based material or bioglass, they have quite high fracture toughness when compared to the remaining ceramic material like bioglass, ceramic, calcium phosphate, silica, hydroxyapatite. So, eggshell you can see it has got very low fracture toughness, we are all used to that, right. If there is a crack, immediately it fails. some of your bone material, high density, low density cancellous bone have very low Young's modulus as well as very low fracture toughness. So, the fracture toughness of most of the ceramics are low, whereas the compressive Young's model for strength is high. Once again this picture you can see, this is a material, ductile material, this is a brittle material, this is the bone. Brittle fails before permanent deformation like ceramic, ductile deforms greatly before deformation. Bone can exhibit both. Okay. So, brittle material will not show any ductility, it will fail. Okay. This is an interesting table again, because we are comparing different materials with your bone. As you can see, bioglass tensile strength is comparable to the bone, elastic modulus is also okay, poor fracture toughness, compressive force strength is very high. Hydroxyapatite, if you look at it, it is also comparable to cortical bone, compressive strength is very high, elastic modulus is also high, fracture toughness is extremely low. Alumina, you can see here. Stainless steel, if you see, the fracture toughness is high, elastic modulus is very high when compared to your bone. Titanium of course is much less than your stainless steel, but still even that has very high elastic modulus when compared to your cortical bone. Okay. So, this table compares different metals as well as the ceramics like hydroxyapatite, alumina, bioglass with the bone. Okay. This was taken from this particular reference. Okay. So, these biomaterials, ceramics are widely used mostly in dental and in orthopedic application like total hip, artificial total hip, knee, high density alumina, metal, bioglass coatings. Basically they are coated so that the metal on metal interaction does not take place, which may lead to debris formation, metal leaching and so on. Bone plate screws, they are all coated with bioglass, polysulfone, carbon fiber composites. If you look at intramedular nails, again this is an orthopedic I showed long time back, we can have bioglass coating, rods, permanently implanted artificial limbs, again you have bioglass, carbon fiber composite, vertebrae spacers, alumina, spinal fusion bioglass, alveolar bone replacement, mandibular reconstruction, we have PTFE, porous alumina, bioglass, dense apatite and osseo-tooth. Okay, this is teeth related, alumina, bioglass, dense hydroxyapatite, orthodontic anchors, bioglass, coated alumina. Again you see, as you can see generally bone related places, fillers, coating and then some teeth related, tooth and orthodontic anchors and so on. This information is got from this particular reference. Okay. So, once again we can see alumina, zirconia, graphite, carbon, different hydroxyapatite, bioglass, glass. So, Young's modulus varies a lot. Okay. So, very low vitreous carbon, pyrolytic carbon, okay, hydroxyapatite 73, okay, and going right up to inert alumina 380. The compressive strength, if you look, carbon is comparable to the bone material, where hydroxyapatite is quite high. Okay. So, these table shows you how each oxide varies, and carbon seems to have reasonably good properties when compared to the bone. Hydroxyapatite comes here, okay, and your bioglass comes here 75, but it has got a very high compressive strength. Okay. So, let us look at little bit on each one of these biomaterial. The oxides, that is the alumina, aluminium oxide it is called Al2O3, it has got density of 3, bulk modulus, compressive strength. This is used as a biomedical material early 1970s in both high density, high purity polycrystalline and single crystal forms actually. Okay. And this is the range of densities or modulus or compressive strength. It is used in osseous tissue ingrowth to stabilize prosthesis in the skeletal system, polycrystalline alumina and sapphire in dental application. So, as I mentioned mostly you will find in fillers, bone replacement coatings in the orthopedic and in filling in the dental. Calcium phosphate ceramics is called CPC, it is used bioceramics as hydroxyapatite, okay, and beta tricalcium phosphate. So, calcium phosphate is used as hydroxyapatite or beta tricalcium phosphate. The hydroxyapatite has the chemical formula, we have the calcium, we have the phosphate and the hydroxyl group. Generally the calcium to phosphorus ratio will be 1.67. So, again calcium phosphate, hydroxyapatite, as you know, is widely used in bone filling because the bone is predominantly calcium phosphate. So, the osseointegration happens very comfortably. If you look at zirconia, zirconia is finding a good application of late. It has got very good mechanical strength and fracture toughness because the rest of the ceramics have very poor fracture toughness, whereas zirconia is quite good. So, it is used in the total hip replacement THR, total hip replacement ball heads. Okay, there is a ball and socket, you may have metals, in order to prevent metal on metal they may coat it with zirconia. So, it prevents the wear and also it has got good osseointegration properties. So, it integrates very well with the bone tissues, okay, it is very biocompatible. So, total hip replacement ball heads, total hip replacement acetabular inlays, total hip replacement condyle, finger joints, spinal spacers, humeral epiphysis, hip endoprosthesis. So, all these places where you have ball and socket type of moving zirconia finds application. So, alumina and zirconia have very good applications in orthopedic and dental applications, but zirconia is coming off late because it has got much better fracture toughness than any other ceramic, bioceramics. Bioglass, when we say glass it is mostly silica, that is why it is all generally you will find a silica based material, okay, SiO4, 4 minus, they have found places in prosthesis actually. They are embedded in a biomaterial support to form prosthesis for hard tissues. Such tissues are biocompatible, they show excellent mechanical properties and are useful for orthopedic and dental applications. Okay. And bioglass is generally silica based, different types of combinations of silica will be present. So, you can also think of composites made of bio-inert and bioactive ceramics. So, each can do certain activity. So, we can achieve bioactivity and bio-inert can give you the mechanical strength. Okay. So, composites of these inorganic materials are also being looked at actually. So, alumina ceramics are used with hydroxyapatite. So, hydroxyapatite may have poor properties, alumina may have better properties, whereas hydroxyapatite is bioactive. Okay. So, we can combine these two properties to form composites. Of course, we can even think of coating metals with hydroxyapatite or bioglass, so that you get good osseointegration and bioactive property when compared to the metals. Again, we can prevent atmospheric oxidation related corrosion of some metals by coating hydroxyapatite on top of metal joints. So, there are so many options available by bringing in ceramics into the picture of biomaterials. Okay. Let us look at one simple problem in the area of the ceramics. Okay. Imagine we have a stainless steel here, it is a rod used in say orthopedic application. This is a 10 millimeter diameter stainless steel rod, it has got a Young's modulus of 200 gigapascal, strength, yield strength of 300 megapascals, density of 7.9 gram per cc. Okay. This is the stainless steel. So, they coat it with 1 mm thick bioglass. Okay. Bioglass has got good integration property, stainless steel may corrode also. So, assume you are coating it with 1 mm, Young's modulus is 300. So, as I mentioned it's quite the Young's modulus can be very high for ceramics, but then it does not have a plastic region at all. It has got 300 megapascal fracture, density is 4.5 grams per cc. So, it just okay. Fractures as soon as it reaches this. So, there is no ductile region at all for ceramics. Now, the question is, what is the Young's modulus of this composite? Of course, we can use this mixture rule, right. E1 V1 plus E2 V2 is equal to U1 A1 plus E2 A2, that is V1 is volume fraction, V2 is volume fraction. So, we can put the areas into the picture, area fraction, okay. Okay, so what do you do? Area of this stainless steel rod, it is a 10 mm diameter stainless steel rod. So, pi r square is the area, pi into 10 mm dia. So, 5 mm is the radius, okay, 10 power minus 3 multiplying to make it into meter square. So, you get meter square. So, we have 3.141 into 25 into 10 power minus 6 meter square. So, the area of this stainless steel rod is pi into 25 into 10 power minus 6 meter square. We are converted into meter square because we have this Pascal, we want to bring it there. 10 mm is the dia, so we made it 5 mm. Now, you have 1 mm thick coating of bioglass. So, how do we calculate the area of this bioglass? In school you must have studied, we calculate the area of this big one, area of this one and subtract, that will give you. So, pi big one r square minus pi small one r square. So, by big one r square minus pi small one r square. So, now big one is, it is a 1 mm coating, okay, its radius is 5. So, it becomes 6, 5 plus 1 is 6, 1 mm thick. Now, this inside is of course 5 here, right. So, pi into 6 10 power minus 3 raised to the power 2, this is for converting into meter, minus area of this rod which is 5. So, when I do this, 6 square is 36, 5 square is 25, 36 minus 25 is 11, 10 power minus 3 square is 10 power minus 6. Okay. So, you get the area of bioglass, that is this portion as pi into 11 into 10 power minus 6 meter square. Area of the stainless steel rod is pi into 25 into 10 power minus 6 meter square. So, the Young's modulus we can calculate a fraction, right. 200 is for the stainless steel, 25 is the area divided by 25 plus 11 is 36, that is the fraction of area. And then the Young's modulus of this bioglass is 300, area is 11, total area is 11 plus 25, 26, sorry 11 plus 25, 11 divided by 36. So, this 200 comes for the stainless steel, the area of stainless steel is 25, the total area is 25 plus 11, that is 36, plus the 300 comes from the Young's modulus of the bioglass, area of the bioglass is 11 divided by total area is 25 plus 11, 36. So, when we calculate that, we end up with 230.5 gigapascal. So, the Young's modulus of this composite is 230.5 gigapascals. Okay. We use the mixture rule, and Young's modulus of stainless steel into volume fraction plus Young's modulus of bioglass into volume fraction. So, instead of volume fraction we can use area fraction because we do not know the rod length. So, it does not matter. So, area fraction is area of the stainless steel divided by the total area, here area of the bioglass divided by the total area. Total area is area of stainless steel plus area of the bioglass. So, 25 plus 11, that is why we have 36 here. Okay. Now, the second question is, what is the average density? We can do it in the same way, with the density of stainless steel is given here, density of bioglass is given here. So, we can do the same thing, 7.9 multiplied by 25 by 36 plus 4.5 multiplied by 11 by 36. Okay. We use the same approach, area fraction for stainless steel, area fraction for composite. So, that comes to 6.86 grams per cc. Okay. Here we use mixture rule, which is like both contribute based on their volume fraction or area fraction, but in real case it might not be so actually, because if you remember, there is another rule called Roy's rule we studied long time back, where the equation is slightly different. So, you may get a slightly different answer if you use that particular rule. Okay, let us proceed with the problem. Same problem, what is the maximum strain the composite can carry? So, we have now a stainless steel rod which is coated with bioglass, and imagine it is pulled. Okay. So, what will be the strain? Both of them will have different strains depending, because the Young's modulus is very different. So, how do we calculate the strain? So, we do stress by strain is equal to Young's modulus. Okay. So, stress divided by the Young's modulus. Okay. So, we have for the stainless steel 200 is the Young's modulus gigapascal. So, we convert into Newton by meter square. Okay. For the bioglass it is 300. So, 300 into 10 power raised to the power 9 Newton per meter square. Okay. And imagine we are putting in stress of 300. Okay. Because stress by strain is equal to Young's modulus. Okay. This is the stress. So, we divide this stress by the Young's modulus to get the strain. Okay. And same stress is divided by the Young's modulus to get this strain. Okay. So, we end up with the maximum strain for stainless steel is 1.5 into 10 power minus 3, maximum strain for bioglass is 1 into 10 power minus 3, but then maximum strain the composite can take will be the lower of these two, because by the time when the strain reaches 1, if it slightly exceeds, the composite will fail, because bioglass will fail. So, the material can take lower of these two, which is equal to 1 into 10 power minus 3. Okay. So, that is the maximum strain the composite can take. Okay. So, how do you calculate this strain? As you know, stress by strain is equal to the modulus. So, stress by the modulus is equal to the strain. So, imagine if you are applying stress of a certain value, this is the modulus for stainless steel, and this is the modulus for this one, okay, bioglass. So, we end up with that. Okay. And so, how did we take, why did we take this 300, and this is the yield, and here also this is the fracture. Okay. So, the numbers are same. So, we put this here, but the moduluses or moduli are different. So, we will end up with different strain values, and as I mentioned, we always have to take the lower of the two strain values, because it is a composite. Once it reaches this value, the composite material will start failing. Next part, what is the maximum load the composite can carry in the axial direction? So, we will assume this as our strain. Okay. Maximum load the composite can carry in the axial direction. Okay. Load, as you know, force by area is equal to stress. Okay. So, stress is the modulus into strain. So, stress for stainless steel is equal to, so we have 200, okay, into 10 power 9, we will use this. So, this is 1 into 10 power minus 3. For the bioglass, okay, we will take the modulus 300 in 10 power 9, again we will take this as a strain. Okay. So, we end up with two different stresses. Okay. Stress is given by this relationship, force is equal to stress into area. Okay. For stainless steel, so we take this as the stress, and this is the area. If you remember, last time we calculated. For the bioglass, this is the stress, this is the area we calculated. So, we get this particular, the force on stainless steel will be this, the force on bioglass will be this. So, the combined force will be sum of these two. So, it is 26.1 kilo Newton. This is the combined force this particular material can take up. Okay. So, you understand this problem. So, as you know, you may get different strains, but the point is we have to take the strain which is the lowest, and then use that in the next step. Okay. So, we calculate stress is equal to modulus into strain, this is the strain. So, we end up with this stress for stainless steel, stress for bioglass, force is equal to stress into area. We calculated these two area from the previous slide. So, we get different forces, when you add up, this gives you the combined force. okay, maximum load the composite can take in the axial direction. Okay. But then there is a problem, generally we cannot use bioglass with stainless steel. Why? Can you tell me why it is? They have a different coefficient of thermal expansion. Okay. So, stainless steel has much higher. So, if there is a change in temperature it will expand, whereas bioglass will not expand. So, there will be a crack. So, there will be a poor bonding between these two material, that is one point. Another one is there will be very different thermal expansions. So, when there is a change in temperature, your stainless steel will expand, bioglass will not expand, so it will break. And then of course, bonding between bioglass and stainless steel is also very poor. Okay. Thank you very much for your time.